Hey class, and welcome to part 5 of Building Envelopes in HVAC. This section will be going over how heating and cooling is delivered within spaces and controls that might be able to save some energy. So there are a couple of different ways to provide heating and cooling to a building that needs it. One is through something called a DOS, or Dedicated Outdoor Air System. In this, you are basically dividing the heating and cooling needs of the space from the ventilation needs, right? People still need to breathe fresh air. So in a dedicated outdoor air system, 100% of the air that's coming into the building is pure, fresh outdoor air. All the return air gets exhausted out. We might have some heat recovery on that, trying to recapture some of the heating or cooling coming out of the building. But we're not trying to heat or cool the space with this air, right? We're just trying to provide fresh air. The heating or cooling will happen from little terminal units inside the spaces. This could be a heat pump, a VRF cassette, even like an electric baseboard. But the idea behind a dedicated outdoor air system is you're dedicating outdoor air just for ventilation, and you're providing heating and cooling another way. That's great, it's very energy efficient. It's also not super common in commercial buildings. What's most common, and what I'll be focusing on, is variable air volume systems, which you're kind of mixing your ventilation needs with your heating and cooling needs. So if the room needs cooling, you bring in a whole bunch of cold air. If it needs heating, you bring in a whole bunch of hot air. And in the meantime, you're also mixing in some outdoor air for ventilation. So that's a variable air volume system in a nutshell. If we look at the actual components of it, this is just a very simplistic diagram, if you will, but we've got some return air coming back from the space. This is probably about 72 degrees or whatever the set point is within the space. We'll exhaust some of that, but we'll also recycle a lot of it. And we'll recycle that air because it's pretty close to the set point that we want, and only bring in a little bit of outdoor air as needed for ventilation. This all gets mixed. This is our mixed air, and we cool or heat that as needed, and then blow that into our building. All right, so this is basically a diagram that's a little bit more complex that you would see on a cut sheet from a rooftop unit. All the components are there, including the different sensors. We've got return air, we've got a damper, which is a way of closing off or opening up the vents, if you will, to mix in more or less return air. Then we have our outside air, it gets mixed. We have cooling as well as heating coils, and then our big supply fan. On the roof, this is what they look like. These are packaged rooftop units for the most part. These will send that air into the building, and it gets sent into the building to a VAV terminal box where it's then reheated to a certain point. So outdoor air coming in might have some humidity in it. It might be raining outside. We don't want to bring all that moisture into the building, so we actually cool it down to a deck temperature or supply deck temperature of around 55 degrees. Looking back at our diagram, so we've got outdoor air coming in. We're going to cool that air down through to 55 degrees, regardless of what the outdoor and return air conditions are going to be. And then at the terminal unit, we'll probably heat that back up again. And we'll do that for each zone, depending on the heating or cooling needs within the space. This, if you're looking at it just up inside the ceiling, like a drop ceiling, it's just going to look like a box with some ducts coming out of it. The rooftop unit, it's often all packaged in. You'll see some of the fins for the condenser, and vents for where the outdoor air is coming in. But it can be a little bit opaque and intimidating the first time you kind of walk up to it. Here's what it looks like from a building operator's perspective. So if a building has an energy management system or building management system or building automation system, sometimes you'll have this nice graphic screen which shows you in real time how the building is actually operating. So you can see what the return air temperature is. you can see what percent of the return air we're actually recycling versus bringing in some additional fresh air versus our minimum ventilation air. Then we have our heating coil, our cooling coil, and supply fan, and then coming out of it is our deck temperature, which in this case is at 63 degrees. So for supply air, if we're in heating mode, we want to bring in warm air to heat up the space. That might be about 85 degrees, maybe 55 degrees for cooling down the space. But the actual deck temperature doesn't vary all that much. It's going to be between 50 to 65, generally closer to about 55 degrees Fahrenheit in this particular climate. So for cooling, that's great. We don't have to do anything to it, right? We use our main cooling coil at the main air handler to cool that down to 55 degrees. But if we're heating, what we have to do is then reheat that up to 85 degrees at the terminal unit deep inside the building in the zone itself. All right, and so that's why set points and setbacks have a really big impact on energy usage, depending on how much reheat you're doing and how much airflow you have coming into the space. So pretty straightforward, programmable thermostats. They work great in theory. In practice, they often get overridden. So make sure that the setback temperature, right, when the building is unoccupied, you don't need to condition it to, a comfortable point. Make sure that the pipes don't freeze and the surfaces don't cool down too much or overheat. But generally during the summertime, it should ideally heat up a little bit. We shouldn't waste cooling energy if nobody's going to be in the space and there aren't any loads or say pieces of equipment that need to be kept at a certain temperature. So make sure that the set point is reasonable. It might have a range, say between 70 to 75 degrees, where no heating or cooling is required, and that the set back temperature is enabled. One thing you want to be careful about is when you're doing an audit, and this is really useful looking at it from a building automation perspective if you have access to this data and the screen, is to make sure that you're not doing simultaneous heating and cooling at the plant level. So if, say, we have 55 degrees air here, that we are turning our heating coil off, because we wouldn't want to heat that up to, say, 70 degrees just to cool it back down. That shouldn't happen in theory, right? That's not how it's designed to operate. But sometimes the valves get stuck and you will still get this hot coil, sometimes steam, passing through this all the time, all year round when it's not needed. So that's one point to check within an energy audit, is to make sure that you don't have simultaneous heating and then cooling at the main rooftop unit or plant level. When you're actually walking around inside the building, you can also have simultaneous heating and cooling within the same zone, or maybe it used to be two separate rooms within the office with a dividing wall that's since been taken down. And so you've got basically the battle of the thermostats, where the diffuser on one side is supplying hot air and the diffuser on the other side is supplying cool air, and the two of them are fighting. Not ideal for saving energy. So you can identify that using a little IR gun and kind of direct the beam basically inside the duct to see what the supply air temperature is. You can also use an infrared camera if you have one of those. If all of the diffusers in the zone look like they're all hot or all cold or all neutral, great. But if you have a mix of the two, then you might have some issues if they're all within the same open area and they're sharing an airspace. The other thing that can happen is the outdoor air damper can get stuck open, right? These vents can get jammed, or maybe the program has been overridden. It's great to have fresh air. I'm all for it. Sometimes these can get programmed shut all the time, which isn't all that great for the people working in there. So make sure that it's still providing a minimum amount of fresh air, but you don't need to be providing fresh air for just the carpets and the empty chairs in the office at night. So make sure that you have the outdoor air damper closed when unnecessary so that you're not spending extra energy to heat up or cool that down if nobody's going to benefit from it at night or during unoccupied times. So 4 main savings when looking at a typical all-air system in a building. Make sure that the setbacks are actually functioning, that not all the thermostats have been overridden, and they're working as expected. Look at the deck temperature. Make sure that that's not going way outside of a range. If the supply deck temperature is at like 35 degrees, then those terminal units are spending a lot of extra energy constantly reheating that. Same if it's up at 75 degrees, you might get too much humidity within the building. Look for simultaneous heating and cooling. See if the cooling or the heating valves are stuck open. If they're both open at the same time inside the main plant, that could be a problem. Also check for it within the zone in open areas and make sure that you're only ventilating and providing fresh air when required to, and you're not spending extra energy conditioning outdoor air if no one's going to appreciate it. All right, that wraps it up for now. I look forward to seeing you next time.